thank you for having me. Thank you for the introduction. I'm going to present you a bit about the paper. You can read, of course, in the proceedings. I would be happy to get feedback from you. The topic I'm talking about is how to relate geometry descriptions to their derivatives on the web using linked data, basically. So I've got an outline for you, beginning with the current problems, then talking about how we can achieve unified linking, how to support multiple geometry descriptions for the same object, because as Johannes kindly said earlier, that is an issue, especially in the planning phase. Also keep track of version history, and finally how to actually connect to the derivatives. Beginning with my background. My background is in link building data. I don't know if you've already heard of that. We're using semantic web technologies and linked data to make the building environment a better place, to our opinion at least. And we have already managed to do a lot of things. For example, to describe products, we have some ontologies, or to describe the building itself, we have the IC OWL serialization, we have BOT for the topology, we have stuff for the properties like the OPM and the CES ontologies, and sensor data, of course, but as we all know, building information modeling also needs, at least sometimes, or most of the times, geometry. And we don't have anything for that in the semantic web. So we need unified methods to link to geometries from the linked building data. So we can describe geometry differently. We could describe it in an RDF graph itself, which is rather verbose and not that effective currently, so it's just one alternative. The other alternative would be to have some snippet included inside of the graph as just a property. So you can imagine this would be some OBJ geometry description, for example. Or you could most easily just have a link to a file that you also provide online. And this is the three different types you can describe geometry with, and link it to a non-geometric description in the semantic web. But as you can see, you need different relations for that. But they should be still the same to ease querying. So this is basically the point where we are starting with. And before I'm going to go to the solution, I will also talk about this one definition from the side of the semantic web versus the side of BIM, common BIM geometry descriptions, which would be in BIM, you usually have the geometry and you attach the information to the geometry. In several cases, this is not needed or feasible. In the semantic web context, it's rather different. You have the object, and this object will have the properties and it will have the geometry. But the object is the center, not the geometry. So we're not having the geometric skeleton, but rather geometry as a property. So if you have this idea, you could, for example, also start thinking about having multiple geometry description, because the information is not anymore attached to the geometry itself. So to allow this unified linking with all of the benefits of the semantic web, we developed an ontology, and we called it the Ontology for Managing Geometry, in short, OMG. This is a rather small ontology because we don't want to reinvent the wheel. So we only have 4 classes and 14 properties to define geometry, or not define geometry description. Sorry, that's not the scope. To link to geometry descriptions. We're also trying to reuse already invented concepts. So we're not doing the same effort over and over again, but we're also visible from the other perspective of the semantic web. And then we also introduce 3 different levels. So everyone who's applying the OMG can decide on themselves in which detail they want to use OMG. The first level is basically just to create a unified linking between an object and its geometry description. And the second level, we reify this property and we create an additional node which allows you to add metadata to every geometry description and therefore have multiple geometry description for the same object with being able to differentiate between those descriptions. And level 3 goes even further. With introducing a geometry state, we allow to keep track of the version of the geometry description. And a part of these levels, we also provide concepts to connect to derivatives, which could be, on the one side, two geometry descriptions that can be calculated from each other, or one that can be calculated from another. For example, you have the geometry of the chair, and you can create a bounding box of it. And you maybe don't want to create the bounding box every time you need the bounding box, but rather store it. But then you need the link between the geometry description of the chair and the bounding box, because if the chair changes, so needs to change the bounding box. And finally, also something we are introducing in the OMG is a grouping mechanism, something like tagging the geometry descriptions themselves to allow you to just say, I want to have all geometry that is relevant for daylight simulations, for example, to easily extract from the multiple geometry descriptions exactly the ones you need. So that's the basic concept. I'm going to show you the technical implementation now, so I'm not going to talk a lot about the details because we have to watch the time, but so you see everything. If you have questions, please ask them. I have a lot of text on the slides on purpose, so you can go through the slides later on again by yourselves. So let's go. With level 1, we're starting. Here you can see you have the object, which is the focus point of the linked building data, and RDF-based geometry descriptions or snippets or URIs. And we have two different relations to connect. One is specifically designed for objects, so to connect two nodes, and one is specifically designed to add a value to an object. They are very generic. You don't have any idea about what kind of geometry schema you're using. What is the content of this, for example? Is it OBJ or GLTF and so forth? And then on the second level, here you can see it's basically the same as the first level, except there's these nodes in between, geometry 1 and geometry 2, which are of type geometry. And here you can add metadata. For example, saying this is my bounding box and this is my detailed description. And this metadata you can, of course, also add this geometry context tag to it. And this is a unified relation, so you can, with one query, extract all of the geometry descriptions of an object in disregard whether it is RDF-based or not RDF-based geometry descriptions, to allow easier querying. And then we are going to the third level, where we have next to the geometry node, the geometry state node. And the idea is basically that every time the geometry changes, you create a new geometry state. And the old geometry is not overwritten, or it's not deleted, but you can give the geometry state a tag that it's deleted. And here you can also see how you could use a grouping mechanism as the geometry context. So that were the levels. Now we're talking about the definition between the relations between dependent geometry descriptions. Here you can see you have relations between two geometry nodes, and we differentiate between three different relations, which is the derivation, meaning I can calculate this geometry from the other. The transformation, for example, there are 100 chairs or something in this, not this room, but this floor. I don't want to have the geometry description 100 times. I just want it once, and I want to transform it to different positions. And also complements, for example, for details. Yeah, I'm currently not having a good example. I think Mathias might have one later in his presentation following up. It's for a geometry that's not valid by itself, but it complements another one, and you can load them together, basically. And then we also have the derivation of properties, where we are using another ontology for property management. There you have direct and indirect connections which you can model. Overall, this is a basic overview. What can you do with the OMG when you're using which level? And there you can see until the versioning, this is all kind of depending on the, here's the versioning. This is kind of depending on the level you're using, while the derived properties are independent of the levels. Here's some more links and information about where you can find the ontology and its documentation. And with that, I'm concluding. We have a unified linking method. We can handle multiple geometry description. We can track version history, and we can define the dependencies in between. However, it's very generic. We cannot differentiate between the schemas we are using. And some of the concepts we are introducing in this ontology should probably be part of another ontology because it's on property level. And also, we only provide means to define that there are connections and derivations. We do not define how to calculate the different geometries and properties from the geometries. So there's also something that we need to dig into. And with that, I would like to thank you for your attention, and I'm open to questions.